This is the 17th video in our series on Lie algebras. And today we're going to look at some natural copies of SL2 inside of any semi-simple Lie algebra. Well, I should say finite dimensional complex semi-simple Lie algebra. Okay, so throughout this video, we're going to fix the following notation, and this actually notation will be fixed kind of from now on. So L is a finite dimensional semi-simple Lie algebra over C. H is a Cartan subalgebra of L. Remember, that means that it's an abelian subalgebra containing only semi-simple elements, and it has maximal dimension across all subalgebras with those other two properties. Then furthermore, we'll take Phi to be the set of all alpha in H star, such that alpha is not the zero map and L sub alpha is not the zero vector space, where L sub alpha is the root space of the root alpha. So these alphas are called roots. And so what I mean by that is it's all x in L such that if we take the bracket of h with x, we get alpha evaluated at h times x. And that's true for all h in h. Recall that H star is the set of all linear combinations from H to the complex numbers. That's why this makes sense right here. Okay, so now I'd like to make a quick observation about this root space decomposition that follows from what we did last time. And well, several times ago, we had the following root space decomposition. So we wrote L as L0 and then plus the direct sum over all roots, so we've got alpha and phi of L sub alpha. But now I'd like to maybe make that a little bit nicer to extend the dependence on H. Notice that the dependence on H is inside of this already, given that this phi is built out of things from H star. But now I'd like to notice that L sub 0, well, what is that? That's going to be all x in L such that h bracket x is equal to, well, notice that it's going to be 0 times x. In other words, it's going to be 0. And this is going to be for all h inside of h. But there's a name for this, and that is the centralizer in L of h. But then let's recall in the last video, we proved that the centralizer of L in H is in fact equal to H, this Cartan subalgebra. And so that gives us this more classic version of the root space decomposition, where we would have L is equal to the Cartan subalgebra, direct sum with, well, the big direct sum over all of these roots of the root spaces. So something like that. And now I'd like to point out that here we're using this notation where capital L is a Lie algebra, and then like this capital H is a Cartan subalgebra, and so on and so forth. But there's another kind of standard notation where we use this fancy G as the Lie algebra, and then the Cartan subalgebra is this fancy lowercase h. And then, well, the rest of it's kind of the same. So we would have plus over the direct sum over all of these roots of G sub alpha, where G sub alpha is defined exactly like this L sub alpha over here. Okay, so now that we've done all of this, let's maybe go ahead and start to look at natural copies of SL2 inside of L. I think we've seen so far that SL2 is a very important Lie algebra to study, and well, it's probably even more important than we're able to understand given what we've done throughout these videos. But we're going to extend kind of our knowledge of its importance as we move forward. And we'll see that we can essentially build any Lie algebra out of kind of SL2 parts. And we're going to start looking at that today by seeing natural copies of SL2C inside of any, well, finite dimensional semi-simple Lie algebra over C. And let's do this maybe via an example first. And after doing this via an example, we'll like prove maybe a general result. So let's think about SL3C. So recall that that's going to be the set of all trace 0 3x3 matrices. So we might write it like this. X is inside of GL3C. So that's just all 3x3 matrices, such that, like I said, the trace is 0. That's the sum of the diagonal elements. And now let's look at the following 3 subspaces of SL3. So I'll just write them via their basis, so the span of their basis elements. So let's take this first one, which has 1, -1, and 0 on the diagonal in that order, and then 0 everywhere else. And then our next element will be 0, 1, 0, 0, 0, 0, 0, 0, 0. So in other words, it's got a 1 in that first row, second column. And then, well, the transpose of that. So it's got a 1 in the second row, first column. Now, you can check that this forms an isomorphic copy of SL2C inside of SL3C, where this first matrix is playing the role of H, and then E, and then F over there. And then that's pretty easy to check. In fact, I think we've seen this before. And then maybe we could look at another one. There are actually 3 natural ones here. So the next one would be like this. So we've got 0, 1, -1 on the diagonal, 0 everywhere else. And then we have, let's see how it goes. It goes like 0, 0, 0, 0, 0, 1, 0, 0, 0. So that's going to be a 1 in the third column, second row, and a 0 everywhere else. And then the transpose of that. So let's see, that's going to put a 1 down there. And then, like I said, that's also a natural copy of SL2C. And you can check that that has the commutation relations of SL2. And then maybe there's like one more natural one, which has a H matrix of 1, 0, -1. And then let's see, the E matrix will be 0, 0, 1, 0, 0, 0, 0, 0, 0. And then, well, the transpose of that will be the F matrix. So let's see, it looks like this. And, well, you can also check that this has the same defining relations of SL2C. And then, well, if we saw that this is happening in SL3, I think you could probably generalize this to SLN pretty easily. And in fact, you can find lots of copies of SL2 in, larger n values of SLN. Obviously, it's going to depend on the value of n. Okay, so now let's move towards finding copies of SL2 in an arbitrary Lie algebra satisfying these conditions. That'll begin with this proof that says if alpha is a root, then minus alpha is also a root. Remember, this is the set of all roots over here. Okay, so let's see how that goes. So let's say given alpha is a root, in other words, it's in this capital Phi, that means that there exists a non-zero vector x inside of L alpha. So since it's inside of L alpha, what does that mean? That means that the bracket of h with x is equal to alpha evaluated at h times x, and this is for all h inside of that Cartan subalgebra. Remember, we fixed everything over here. Okay, nice. And now, well, let's recall the following. So L semisimple is equivalent to this killing form. Remember, we've been using the killing form for the last several videos, being non-degenerate. So, well, it's equivalent to that. Well, so that means that it implies the killing form is non-degenerate. But then by the definition of non-degenerate, that means that there exists some y inside of L such that the killing form of x with y is not equal to 0. So, well, what are we going to do with that y? So now we're going to do the following. So let's write y via its decomposition from this root space decomposition. So we can write y as, maybe we'll write it as y0, and then plus the sum over all alpha in this phi of y sub. I'm actually going to change that to beta instead of alpha because we've used alpha up here for this special one. And then I should point out here that y naught is inside of h, whereas y beta is inside of L beta. You know, again, like this root space decomposition. Okay, so now let's apply the killing form again using this root space decomposition, and we have 0 is not equal to the killing form of xy, because that's like our assumption up there. But the killing form is a bilinear form, so that means that, well, we can split it up via this sum. So that's going to be the killing form of x y naught plus our sum over all beta in phi of the killing form of x with y beta. So something like that. But then this whole thing over here being non-zero means that at least one of these terms is non-zero. That's because, well, they're all linearly independent. And so, well, that means that one of them is non-zero. So, but that means that the killing form of L alpha L beta is non-zero for one of these L betas. So I guess I should say that this will give us 0. You can check that. That's something we proved earlier. But recall that that killing form being non-zero implies that beta equals minus alpha. That means that minus alpha is one of these things in the roots. It's exactly the only one that's producing our non-zero portion of the sum. But, well, that's exactly where we wanted to end up, is that minus alpha is inside of this. All right, so now we're ready to build our copy of SL2. Okay, so here we have it. The proposition will read as follows, producing our copy of SL2 inside of L. So if we take an alpha inside of phi, in other words, alpha is a root, then that means that we can find non-zero vectors x in L alpha, y in L minus alpha, such that the two following things occur. So the bracket of x with y is non-zero, and the span of x, y, and bracket of xy is isomorphic to SL2. Okay, so let's see how this might go. We're going to prove that this bracket of xy is non-zero. Okay, so since alpha is not identically 0, so we know that it's not identically 0 because, well, it's a root. And over here, well, that was one part of being a root. So that means that there exists some sort of t inside of h such that alpha evaluated at t is non-zero. Okay, but now what we'll do is play around with the killing form again. So let's do kappa of t with the bracket of x with y and see what we get. So that's going to be kappa of the bracket of t with x and y, just by the property of the killing form that we can move the bracket, well, the way that we just did. But then let's recall that this bracket of t with x is equal to alpha evaluated at t times x, given the fact that t is inside of h and, well, x is inside of L alpha. So, and then I can bring that out because the killing form is bilinear. So we have alpha of t and then kappa of x with y. But then, well, let's recall that we chose t so that this alpha of t was non-zero. And then furthermore, since x is in L alpha and y is in L minus alpha, we know that kappa of xy is also non-zero. That's by a previous result. But now if we take the product of two things that are non-zero, we definitely get something non-zero. But that means that these original two vectors could never be equal to 0. Otherwise, we would get 0 out of this. In other words, we have the bracket of xy is non-zero. All right, good. So we've proven this first condition. Now let's go ahead and prove the second condition. Okay, so now moving on to this second conclusion of our proposition, let's maybe set h equal to the bracket of x with y. And now, well, let's observe that the bracket of x with y is an element of L alpha, L minus alpha. The bracket of L alpha with L minus alpha, just given where x and y come from. But then let's recall that that's going to be a subset of L alpha plus minus alpha, which is L0, which is equal to h. So that means, yes, this bracket xy, which we have named h, is inside of the Cartan subalgebra. So that's interesting. But what that means is that, well, we can apply alpha to h. If it weren't inside of the Cartan subalgebra, it wouldn't make sense to apply alpha to h, given that alpha is inside of h star. Okay, great. So from that, we're going to make the following claim. And that claim is that if we take alpha and apply it to h, we get something that is non-zero. Okay, so let's see how the proof of this claim goes, which we will do via a contradiction. So by way of contradiction, let's suppose that alpha of h is equal to 0. Okay, but then what would that tell us? So that would tell us that h with x is equal to alpha h is equal to 0 times x, which is equal to 0. And the bracket of h with y, well, remember that's minus alpha of h times y, but if alpha of h is 0, minus alpha of h is also 0. Okay, but then what does that tell us? That tells us that the adjoint action of x and the adjoint action of y commute with the adjoint action of h. But let's recall that the adjoint action of h is the adjoint action of the bracket of x with y. But the adjoint action of the bracket of x with y is equal to the bracket of the adjoint action of x and the adjoint action of y. That's something that we proved, kind of a long time ago. But then we also proved that if add x and add y commute with add x bracketed with add y, then that means that this object right here is nilpotent. In other words, add h is nilpotent. Again, by a much previous result. But that is actually our problem. So h is inside of h, a Cartan subalgebra, which tells us that h is semi-simple. Remember that Cartan subalgebras are made up of only semi-simple elements. But semi-simple means that add h is diagonalizable. That's the definition of an element being semi-simple. Okay, so let's see what we have here. We have add h is nilpotent and add h is diagonalizable. But the only thing that's diagonalizable and nilpotent is the zero matrix. But that tells us that we have add h is, well, the zero map. But then, if add h is the zero map, that means that h is in the center of our Lie algebra. Remember, add h being equal to 0 means if you bracket h with anything, you get 0. But that's exactly what we need to enter into the center. But check it out. The center of a Lie algebra is a subset of the radical of a Lie algebra. I think we proved that earlier as well. But then the radical of our Lie algebra is 0, given the fact that we're a semi-simple Lie algebra. But let's read this up. We have h has to now be inside of the 0 subset, which means h is equal to 0. So let's maybe conclude that here. H is equal to 0, but then recall up here, h was equal to the bracket of x with y. but we already proved that the bracket of x with y was non-zero. So that's our contradiction. So we contradicted this fact that h, well, is non-zero, which means yes, we do have this claim proven that alpha of h is non-zero. So let's maybe put a check mark next to this claim, and then we can do the final steps to prove that, yeah, we've got a copy of SL2 here. Okay, so now to finish this like purple dot here, what we'll do is rename, maybe not rename, but define some new vectors which are scalar multiples of the old vectors. So they're going to be like this. So let's set h sub alpha equal to 2 over alpha of h times h. Now we can divide by alpha of h because we showed that it was non-zero. So that was one of the reasons we did that. And then next we'll define E alpha to be the square root of 2 over alpha of h times x. And then finally F alpha will be equal to, well, the square root of 2 over alpha of h times y. And now from here what you can do is check that all of the commutation relations or bracket relations are satisfied. So maybe I'll just do one and the rest will be left as a homework exercise. So let's look at h alpha with E alpha. So observe that we can bring these constants out and we have 2 over alpha h times the square root of 2 over alpha h. And then we have the bracket of h with x. But then let's recall that the bracket of h with x was equal to alpha h times x. Well, the alpha h will cancel this, and we'll be left with 2 times the square root of 2 over alpha h times x. But then that constant times x is equal to E alpha, so we have 2 E alpha. But look, going from here to here is exactly what we need for this H alpha and E alpha to have the right bracket relations for SL2. And then, well, I'll just, like I said, leave it as a homework exercise to check that H alpha F alpha is minus 2 F alpha. And then E alpha F alpha is in fact H alpha. And that'll complete everything we need for this to be a so-called SL2 triple inside of L. Okay, let's go on to another result. So in order to set up the next result, we need to make a remark. So let's observe at the level of vector spaces, we know that H is isomorphic to H star. Well, remember that any vector space is isomorphic to its dual space. I guess I should say any finite dimensional vector space is isomorphic to its dual space. Then we can actually use the killing form to form a so-called natural isomorphism. So in fact, the isomorphism between a vector space and its dual space is not natural. You have to appeal to a basis. This is actually kind of an interesting fact. There is a natural isomorphism between a vector space and its double dual, but not its single dual. But if we're a Cartan subalgebra of a Lie algebra, there is a natural isomorphism, and it goes like this. So it's going to take H and it's going to send it to the following map, which I'll call theta sub H. And how is theta sub H going to be defined? Well, observe that theta sub H needs to be an element of H star, which means it needs to take an input from H and output a number. So let's take the input from H to be H prime, and the output will be kappa of H comma H prime. So it's defined via this killing form. And now let's observe that kappa restricted to H is non-degenerate. So we know that from a previous result that we proved. But what does that tell us? That tells us that the kernel of this map, which takes H to theta of H, is 0, which means it's injective. But then if it's injective and we know that the dimensions are the same, then, well, it has to be a vector space isomorphism. So that makes this our vector space isomorphism. Okay, so now that we've done this little remark setting up the next result, let's look at the next result. Okay, so this next result says that if we've got a root alpha, x is an L alpha, y is an L minus alpha, then in fact, the bracket of x with y is equal to kappa xy times T alpha, where T alpha is the pre-image of alpha, which is an element from H star, under this map that takes H to theta H. So what that really means is that alpha evaluated at H is the same thing as kappa T alpha H, which is the same thing as theta sub T alpha evaluated at H. That's what it means to be the pre-image of H star, or of alpha under this map. Okay, so let's get to it. So let's take an H in H and note the following little calculation. So it's going to go like this. We're going to go theta sub H of the bracket of x with y. And, well, let's observe that by definition, that's kappa of H with x, y, that killing form. Just that's the definition, or that's how this theta map is defined. But then, well, let's do this thing that we've used a couple of times already and bring this bracket over. That's going to be kappa of H bracketed with x and then y. But now we can use the fact that the bracket of H with x, we know that how that works because x is in L alpha. So this is going to be the kappa of, let's see, alpha H times x with y. Okay, great. But then we know what alpha H is, you know, based off this fact that, let's see, T alpha was the pre-image and all of that kind of stuff. So we can, in fact, write this as kappa of, now we have kappa of T alpha with H times x with y, where let's do some underlining here. Here we took, like I said, this alpha H and replaced it with this killing form right here. But now we can bring that out front given that it is a constant. So let's see, we have kappa of T alpha H times kappa of x, y. But then this is a symmetric bilinear form, so we can swap the H and the x, or the H and the T alpha, and then we can bring this kappa xy back inside this. And that's going to leave us with something like this. We have kappa of H and then kappa of xy with T alpha. So something like that. Okay, but then looking at that, that is exactly theta H applied to something. It's in fact theta sub H applied to kappa xy T alpha. But then let's recall that theta was an isomorphism, but that makes it injective. But it being injective means if two outputs are the same, then two inputs are also the same, meaning that those two objects are the same, but look, that's exactly where we wanted to end up. Okay, so now let's move on to an example or two. Okay, so let's look at a little observation of what we can do with this copy of SL2, which can be found inside of any semi-simple Lie algebra. So let's look at what we've got here. So since for all alpha, all roots alpha, we can find H alpha in H, E alpha in L alpha, and F alpha in L minus alpha, where the span of H alpha, E alpha, F alpha is SL2. I'll define that to be SL alpha. Then we can think about L as an SL2 module with the following action. A dot x, so that's the action of A on x, is equal to the bracket of A with x, where A is an SL alpha and x is an L. Remember, you can always think about a Lie algebra, well, as a module over itself, or even as a module over one of its subalgebras. Okay, so furthermore, if M is a submodule or a subalgebra of L viewed as a submodule, which I guess I should say this includes the case when M is equal to L, then Weil's theorem says that M can be reduced completely. In other words, it's the direct sum of a bunch of irreducible SL alpha, or in other words, SL2 modules. So, you know, I guess the takeaway here is that we should be able to take any semi-simple Lie algebra, find a copy of SL2 inside of it, and then use that copy of SL2 to decompose L into irreducible SL2 modules. And that's exactly what we're going to do with the next example. Okay, so now let's start with a copy of SL3. Recall that it's 8-dimensional. I have 9 matrices up here, but notice that one of the matrices is a sum of 2 others. So here we've got the Cartan subalgebra H alpha 1 and H alpha 2. Well, and their sum, which like I said is going to be important, so I've written it on its own, but it's not independent of those. And then based around this H alpha 1, we have an E alpha 1 and an F alpha 1. Those produce a copy of SL2 like we saw before. And then we've got an H alpha 2 with an E alpha 2 and an F alpha 2. And that also produces a copy of SL2 like we saw before. And then an H alpha 1 plus alpha 2. And it's E alpha 1 plus alpha 2 and F alpha 1 plus alpha 2. Another copy of SL2. Now what we'd like to do is take one of these copies of SL2 and decompose SL3 as an SL2 module via that copy. Okay, so let's do that via this S alpha or SL alpha 1. So that's going to be defined to be the span of this H alpha 1, this E alpha 1, and then finally this F alpha 1. Like I said before, that is a copy of SL2. Okay, so now what we really want to do is see how these vectors commute with all of the other vectors inside of SL3. And that'll give us an idea for how this decomposition works. And so you do that just by calculating some bracket relations. So I'm not going to do the matrix multiplication and subtraction. I'll leave that for you. But maybe the first bit we see is that if we take H alpha 1 with E alpha 1, we're going to get what? Well, we're going to get 2E alpha 1. Well, we know all of that because this is a copy of SL2. So we can write these down quickly. So H alpha 1 with F alpha 1 is minus 2 F alpha 1. And then finally, we've got E alpha 1 with F alpha 1 is equal to H alpha 1. Okay, great. But then let's recall that this picture that we had, and the picture went something like this. So I'm going to put an H alpha 1 in the middle. And then over here on this side, I'm going to put an F alpha 1. And over here on this side, I'm going to put an E alpha 1. And then let's maybe put some boxes around each of these. And then furthermore, I'm going to color code this. So let's say the action of H alpha 1 is given by this magenta color. Then the action of E alpha 1 is given by this blue color. And then finally, the action of F alpha 1 will be given by, I don't know, let's say this orange color. Okay, so notice that H alpha 1 will act via, eigenvector eigenvalue relationship. So for instance, what it does is it'll take this H alpha 1 and send it back to itself with an eigenvalue of 0. It'll take this E alpha 1 and send it to itself with an eigenvalue of 2, the F alpha 1 and send it back to itself with an eigenvalue of minus 2. So we should maybe be, producing a diagram that's pretty similar to one that we saw before, but let's keep going. And then if we act on H alpha 1 with E alpha 1, remember via the bracket relation, we end up in the span of E alpha 1. So that means that this is going to take us from this location to the next location. And then furthermore, it'll take us from F alpha 1 to H alpha 1. And then, well, where does it take E alpha 1? Well, it's going to take it to the 0 vector space. And then, well, what does the action of F do? Well, it actually makes everything go backwards. So that's going to take E alpha 1 to H alpha 1, H alpha 1 to F, and then this F is going to be sent down to 0. Okay, but notice that means that this SL alpha 1 is a submodule of the SL3, just given the definition of a submodule. And furthermore, by this picture right here, we know that it is isomorphic to a copy of Well, one of the classic irreducible modules of SL2, which we called V sub 2. So I'll let you guys look back at all the definitions of those irreducible submodules if you need to. So let's put that over here. So like I said, this is going to be a copy of V sub 2. That's because that's the highest weight, if you will. Okay, great. So now let's look at another example. So let's start with E alpha 2. And let's look at H alpha 1 acting on E alpha 2 and see what we get. So you can do a calculation, and maybe I'll let you do the calculation again. You'll see that you get minus E alpha 2. So that's going to be the eigenvalue under this operation. And then, well, what happens if you take E alpha 1 and hit it on E alpha 2? Well, in fact, what you're going to end up with is E alpha 1 plus alpha 2. So it kind of moves you up a little bit. And then furthermore, if you take our last vector from our copy of SL2, F alpha 1, and now if you hit E alpha 2, you'll end up with 0. So I won't do that. But if you hit E alpha 1 plus alpha 2, you're going to end up with some number. Maybe you can calculate that number if you want to, times E alpha 1. Oh, but that means that the vectors E alpha 2 and E alpha 1 plus alpha 2 form another submodule, because you can't get outside of their span by just hitting with these alpha 1 type vectors. So that gives us the following like shorter picture. So let's go over here and we'll have E alpha 2. And then here we'll have E alpha 1 plus alpha 2. And then let's maybe do the same thing that we did before. Let's put some boxes around these like that. And then, well, let's do our eigenvalue eigenvector relationship and observe that E alpha 1 plus alpha 2 had an eigenvalue of 1 based off, let's see, well, I didn't do the calculation, but maybe I'll write that down. If we do H alpha 1 with E alpha 1 plus alpha 2, you end up with E alpha 1 plus alpha 2. You can do the matrix multiplication if you need to. And then this E alpha 2 had an eigenvalue of minus 1. And then, well, let's see, hitting it with an E alpha 1 moved us up. So that would be like going up here. And then hitting it with an F alpha 1 moved us down. Oh, sorry, this should have been an E alpha 2. So that moves us in this direction. And then furthermore, if you move further in either of those directions, you end up with zeros. Okay, so, well, like I said before, that makes this a submodule because, well, if you hit it with elements of our Lie algebra that we're looking at, you don't end up outside of this submodule. But furthermore, it's going to be irreducible, and we know what type of irreducible module it is based off stuff we did before. This is in fact a copy of what we called before V1. So let's get that written down. This is a copy of V1. But notice this doesn't make all of SL3 yet, because all we've taken account of is 1, 2, 3, 4, 5 vectors, but we've got 8 vectors up here. So let's maybe see what happens to the vectors that we haven't worked with yet. Okay, so moving on, what vectors have we not worked with yet? Well, notice that we haven't worked with H2 or H alpha 2, I should say, or H alpha 1 plus alpha 2. We could work with actually either of those because they only differ by adding an H alpha 1. And we also haven't worked with F alpha 2 or F alpha 1 plus alpha 2, whereas we did work with the E copies of those. So let's maybe do the F's first. So let's maybe do H alpha 1 with an F alpha 1 plus alpha 2 and see what we get from that. So if you bracket those, what you end up with is a minus F alpha 1 plus alpha 2. So again, I'll let you do that calculation. It's pretty straightforward. And then if we do H alpha 1 with F alpha 2, what you'll end up with is an F alpha 2. And then furthermore, what you'll see is that if you do an E alpha 1 with an F alpha 1 plus an alpha 2, you end up with some number times F alpha 2. And then furthermore, if you do an F alpha 2 or an F alpha 1 with an F alpha 2, you end up with some number times F alpha 1 plus alpha 2. And then all of the other appropriate brackets that you might do are 0. So that means that this F alpha 1 plus alpha 2 and this F alpha 2 close a submodule. So let's get those on the board. So we've got F alpha 1 plus alpha 2. And then here we've got F alpha 2. And then let's put these boxes around them so that we're consistent with what we had before. And then, well, what happened? So this F alpha 1 plus alpha 2 had an eigenvalue of -1. This F alpha 2 had an eigenvalue of 1. And then after that, the E's moved us up. So E moved us in this direction. And then after going as high as we could go, it could take us to 0. And then the F's took us down. So, and then after going as low as we could go, we got to 0. And so this is going to be another copy of V1. Notice it's like kind of a companion copy to the one that contained the E alpha 2 type terms. Okay, good. And now, well, we've got one more thing. So now we've taken care of 7 vectors inside of an 8-dimensional vector space. So next up, we could either use this space spanned by H alpha 2 or H alpha 1 plus alpha 2. You could take either of those as the basis vectors. So maybe what we'll do is take the H alpha 1 plus alpha 2. And what you'll notice if you do that is if you bracket A with H alpha 1 plus alpha 2, you get 0 for all A inside of SL alpha. So again, I'll let you check those calculations. It's, pretty straightforward. So what does that tell us? That tells us that we have a one-dimensional subalgebra spanned by this H alpha 1 plus alpha 2. And it's got an H alpha 1 eigenvalue of 0. And then let's see, the E will send it to 0. And then the F will also send it to 0. But then that means that this forms a copy of our classic irreducible SL2 module of V0. Okay, so now I guess putting this all together, which we could up here, let's observe that as an SL2 module, that makes SL3 isomorphic to V2, direct sum V1, direct sum another copy of V1, direct sum V0. And there we've done it. We've done this decomposition of SL3 with respect to one of its SL2 copies. Now I'm going to leave you with some homework exercises. We've got 2 homework exercises, which are kind of like the example that we just did. And these are going to be like kind of a lot of work, but I think you'll get some sort of idea for the shape of Lie algebras that we'll see more generally in the future. So the first one is to decompose SL4 as an SL2 module into irreducible submodules, just like we did with SL3. The next one is to look at another Lie algebra called SP4. So that's a so-called symplectic Lie algebra. So it's of the form, it's of the following form. So there are 4x4 matrices, but in 2x2 blocks. So the diagonal blocks are a 2x2 matrix here, and negative its transpose down there. And then you've got symmetric matrices P and Q on the and then you have symmetric matrices P and Q on the off diagonal. Next up, let's set H sub alpha equal to the following matrix. So notice we've got 1, 0, 0, 0 here in the up diagonal. Sorry, in the upper left block. And then negative 1, 0, 0, 0 in the lower right block. And then these are 2x2 zero matrices. So then the exercise is to find a companion E alpha and L alpha completing this SL alpha. And then, well, decompose the SP4 into irreducible SL2 submodules, just like we did in our example and in this first exercise. And that's a good